Howdy. Welcome to seminar. We are in the final stretches, so after today we only have 2 more seminar meetings. And there's going to be an announcement. Seth, are you doing it?
Yes, announcement. The Soil Crops Grad Organization, we're having a paint night this Friday, and everyone is invited. That would be 5:30 this Friday here at Peak. And we would also like to search for new officers for the next academic year. So that would be next Tuesday. It's 12 to 1 at Keep 440. So if you want to run for any position, please let us know, any of the officers on the Soil Crops Grad Organization, and we'll be happy to have you in the group. That would be it.
Thanks so much, Seth. And then one more thing, so Beth is going to come next week, so for the students enrolled, we're going to be taking our class photo. So I'll be sending out an email, but please try to get here about 5 to 7 minutes early so Beth can get a picture of everyone prior to starting the seminar. Okay, is that all right?
Well, I have the pleasure today of introducing my PhD student, Gregory Rouze. He is going to be graduating hopefully this summer. He is co-advised between myself and Dr. Christine Morgan. He has a bachelor's degree in geology from Baylor, but we took him anyways and have now trained him as a soil scientist. He actually got his master's degree here in our department, looking more at passive gamma ray and the spatial variabilities of soil properties. But now his PhD is on UAVs and evapotranspiration. He's been able to travel internationally. He's been to Spain, Australia, and within this project, with such a heavy workload, he's been able to mentor at least 15 undergraduate students. So, with that.
Thank you, Haley. Thanks everyone for attending today's seminar. My talk is focused around using these UAVs. You know, it's a buzzword, right? You hear it a lot. And what I wanted to address today is a proof of concept, how you can use UAVs and the cameras that are on them to estimate evapotranspiration. So a bit of background, just a general problem that we're faced with. I'm going to focus within Texas, really, but the idea is that our population is expected to rise, right? So the Texas Water Development Board released a state plan a few years ago in 2017 that was demonstrating this very idea that over time, here's the pointer, that 2020 will have a population of about 29.5 million, and it's expected to rise up to 51 million by 2070. So when you consider the fact that the farmers may have to do with less in terms of the irrigation that may or may not be available in the future, what that state plan is projecting at least is that there's bound to be an 11% decrease from 2020 to 2070 with the dashed blue line, and the demand is expected to rise, right, because we're expected to increase in population. So we're seeing a divergence of projections, and we're seeing potential water deficiencies, and that's a problem when you consider, at least within the state of Texas, that the irrigation sector, out of all the sectors within Texas, irrigation is the top dog, so to speak. So even though it's a flat line, right, it's still the highest user of water, even against the rising uses from the municipal sector. And one way that we could potentially get around that and improve and optimize our irrigation scheduling is in terms of evapotranspiration and having a good idea of quantifying that information. So what do I mean by evapotranspiration? So that term refers to 2 components. It's the evaporation that comes from the soil, and then it also happens from transpiration through the plants themselves. So this is just a cartoon, but the idea is that the energy balance refers to solar radiation, imparting on leaves and soils, and depending on the vegetation properties and the soil properties, you're going to see two different states going on. You'll see one that's called the latent heat, which is analogous with evapotranspiration. We have a change in state of water from a liquid form to a vapor form. And then the second phase, which is the change in temperature of the atmosphere. So because the soils and potentially the crops are warmer than the atmosphere, that's where that direction is heading in terms of the temperature. So the interesting thing, at least in my opinion, is that you can potentially estimate evapotranspiration using remote sensing, and so it's a broad and vague word, but what that refers to in this context is using various platforms. So we have satellites and manned aircraft in the very beginning of this remote sensing. So here's a picture of Landsat 8 currently. It's still operating in orbit, and it comes around and it surveys a given location in a fixed orbit. And the manned aircraft is not operating in orbit. It flies lower to the ground, so you have a little bit more control. And while that has worked, fairly well for the last 20 or 30 years or so, the problems are, they are multiple. The first of which is that depending on how high you fly above the ground, that's going to affect your pixel resolution, the size of a given pixel. And at least within the context of satellites and manned aircraft, you can have potential problems because it's so far away from the ground. The idea is that you want to separate, ideally, your crops and your soils, and the satellite and manned aircraft pixels, generally speaking, do not allow you to do that. And then the other problem is more in terms of practicality. So if you operate, at least within satellites, say, you come around and you survey a given location at, consistent time, you have that consistency, right? But the problem is that you may have clouds that, that play, I'm sure some of you are familiar with, you can have clouds that degrade the signal that comes from the cameras, and that the variability really is the bigger problem within that context. So that's where the UAVs can come into play. That's why people have been researching this tool. It's been gaining traction within the last 5 years or so for the reasons that you can have more flexibility in getting the data that you want, and at a centimeter scale resolution, as fine as centimeter scale resolution. But the things that I'm interested in, at least, is that while there's been other applications beyond just evapotranspiration, there hasn't been really much proof of concept within the ET modeling realm, and especially within cotton. And that's how I want to frame up my objectives. So they're twofold. So the first one is just, again, a proof of concept. Can we model ET using UAV-based data? And if so, what type of model could we use? So we'll get into this later, but there are many different types of models that can be used to estimate evapotranspiration. Unfortunately, there's no one-size-fits-all method. You can't just plug one in and expect everything to work perfectly, because each have their own set of assumptions and inputs, and again, we'll go over that. But we wanted to kind of, address that question a little bit more clearly. And the second question or objective is, what is the impact of pixel resolution on model ET, right? And I kind of laid the framework, so to speak. You have satellites, which are, very high up in the air. Manned aircraft, you have a little bit better resolution, and with UAVs at the finest. And we kind of wanted to quantify that within a single energy balance model. So getting into the field itself, we're located at the Texas A&M Experimental Farm. It's about 20 minutes away from here. The field itself is shown here on the left. It's just a Google Earth I extracted. And what's interesting is that just from this map alone, you can see pretty clearly the gradient in terms of moving from darker soils on the left to lighter soils on the right, based on the paramaterials that were in the geology that was existing, that is existing at that time. And about 10 years or so ago, one of Dr. Morgan's graduate students conducted what's called a electromagnetic induction survey to get a better understanding and quantify, where these maps could be. Like, the different colors here represent the different signals. So the blue is the higher ECA. ECA refers to apparent electrical conductivity. That's what the sensor is giving us, which is correlated with soil water holding capacity. Again, this has all been done in the past, and what I've been doing recently is kind of making a map out of said ECA survey. And the idea is that the difference in soil types is kind of going to set up for my results later on. So the data that I'm going to present is just for one growing season, specifically in 2017, where we planted the cotton seeds on April 5th, and they were harvested on October 14th. And the harvest date was slightly delayed because of Hurricane Harvey, so for those who are around can appreciate that. The field itself was under a central pivot irrigation system, And what I wanted to point out specifically on this slide are two things. So the top panel, this top plot, is on the y-axis. You're seeing the temperature in terms of degrees Fahrenheit as a function of or plotted against the growing degree days on the x-axis. And the different colors represent different daily temperatures. So the red lines are the daily max, the daily green, and blue, the daily minimum, excuse me. So the different patterns that exist throughout the growing season, we saw a couple of things, at least I did. So the blue line here, you can see it dips under this horizontal black line, and those two horizontal black lines represent the threshold beyond which cotton is not going to grow as well as it could. So we had some daily minimum temperatures that were below that lower threshold, and then we had, during the summer, the late summer, we had maximum temperatures that were going beyond the upper threshold. And the bottom plot is showing not temperature, but rather precipitation, so in millimeters. And again, plotted against the same growing degree days. We saw early rain events, and I pointed out one in particular here. You get a big spike around the growing degree days. And that was basically when the cotton seeds were planted in the ground. And what happened as a result of that is we had some soil crusting, and it wasn't as lush of a canopy as we would have anticipated. But I just pointed out that we have some soil crusting going on as a result of said precipitation. So I wanted to suggest that the UAVs can be used to model evapotranspiration. So the UAVs refer to the platform itself, right? The cameras actually go on those individual platforms. So within the context of my talk here, I'm going to be focusing on two cameras. So the first of which is a MicaSense Red Edge, which collects radiation in the visible and near infrared spectrum. So about 50% of the radiation that the sun imparts on the plants, half of that is roughly from the visible and near infrared. And then on the high end of the electromagnetic spectrum, we have the thermal, which is measured by an ICI 8640p camera, and it detects between 7 to 14 micrometers. And in that region, at least, you have a relatively lower frequency compared with the visible and near infrared. So, we have these cameras, they collect images, and what I want to briefly mention is that you want to take those images and compile them all together, right? Because if you want to at least make it one nice, pretty map, you have to stitch them, and orthomosaic essentially means stitch your images and put them in a coordinate space. So what I did for this is to create 3 different pixel resolutions, 15 centimeters, 1.05 meters, and 10.05 meters, to kind of represent the UAV resolution, the 1.5, which is the manned aircraft resolution, and the 10.05, which is approximately the satellite resolution. So the software for that is listed here. It's from AgiSoft, if you're curious. And the last step that I did for creating these orthomosaics is you have to do a radiometric calibration, meaning that you have to remove the potential effects of the atmosphere that can degrade the quality of the images that come from the camera. So I briefly mentioned in the objective statement that we have all these different models available, right? And what I want to do here is kind of go in a little bit deeper into what those models are. And one of them is called a one-source energy balance model. So what that means is it describes the latent heat in terms of the Rn, the net radiation, the G, the soil heat flux, and H, the sensible heat flux. So this is analogous to the changing the state of the water, and this is analogous to changing the air temperature. So what this means is that in terms of a modeling standpoint, it's going to combine the fluxes from the soil and the vegetation all together, whereas a two-source model, that's where when it says two, that's what it refers to, is it decomposes the equation shown up here into the canopy energy balance equation as shown by a C, and the S, which represents the soil energy balance equation. So the inputs that go into modeling these types of energy balance equations, they actually differ between the two categories. So with respect to the one-source model, it's pretty nice, at least on the surface, because potentially all you would need is just the surface temperature image, whereas the two-source requires all these things shown here. So I put question marks next to these three because what I also wanted to test was, there have been conflicting reports of, how much value do you gain from adding additional weather data input. And so I wanted to see, what value do you gain when you add them and then when you don't have them, and that's what I'll be presenting later on. So you have these things out in the field, maybe you have sensors to a data logger collecting these things. So then what do you actually do? How does that feed into the model or, the different models? So in terms of net radiation, the RN, the weather data would feed in the NDVI. So for those who don't know, NDVI is Normalized Difference Vegetation Index, and that is used to model vegetation properties such as leaf area index and fraction vegetation cover. That feeds into the net radiation component. And then the surface temperature also is used as well, again from the thermal cameras. And the G, or the soil heat, is, at least within this context, is a fraction of the soil net radiation. So you could argue that because there's a diurnal phase shift from between soil heat and net radiation, that generally occurs a couple hours after solar noon, but we collected our images within solar noon, so we feel pretty confident in using a fraction of that solar net radiation. The sensible heat, the H term, is something I don't have up here because that's where the models actually kind of split apart from each other, so to speak. So the one-source model, so the one-source model scales, and what I mean by scales is that it's contextual, meaning that it finds within an orthomosaic, it finds a Tmax, or the highest or hottest pixel, the highest temperature. It also finds the coldest pixel, or the coldest temperature. And when it looks for it, basically what those are defined in the field as is dense vegetation for the coldest pixel, and then like a bare soil for the hottest pixel. And what it does once it finds those end members is that it then scales between said end members for all other pixels that are in the image based on those two end members. And it's funny because this is actually, when the authors published this paper, it's an acronym, right? So it's essentially what it means is deriving atmospheric turbulent fluxes for dummies using temperature. So when I saw the word dummies, I chuckled, internally. But so once and I think the reason why they did that, beyond just trying to be clever, is that they actually want to demonstrate that you only have to use potentially one surface temperature image. So dummies or whatever could just use just one image, and that would be enough, right? So there's a purpose beyond just making a funny acronym. The two-source models, I'll be talking about three here. The first of which is the Precy-Taylor iterative retrieval. So these three models actually differ in terms of how they estimate the HC, or the canopy sensible heat, and then the HS, which is the soil sensible heat. So the Precy-Taylor for the canopy assumes that the plants are completely non-stressed, and based on that assumption, the soil sensible heat, this part right here, uses the assumption from that, as well as the solar noon thermal images and the multispectral, or the NDVI orthomosaics. The dual time difference model is fairly similar to the Precy-Taylor one, in that the canopy sensible heat is, it's indirect, and it's assumed, again, that the plants are non-stressed. But the difference between the two is actually within the HS, or the soil heat. And in the DTD model, the AM survey is actually collected. There's another AM morning, it's like an hour and a half after sunrise. So you collect that in addition to the solar noon image, and that's used to estimate the soil sensible heat. And then the last one, which is the soil canopy temperature, or the TSCV-2T, what that does is it doesn't make any assumptions of temperature itself. It actually directly extracts temperature from a canopy pixel or a soil pixel, and the assumption behind that is that your pixels are fine enough to separate between the canopy and soil. So that's why, and this is actually a relatively new model based on the emergence of UAV platforms, really. So we have these different types of models, and what we want to do is assess how well they are doing relative to our best understanding of the energy flux that's going on in the field. So to do that, we use eddy covariance towers that were installed in that field, and it measures the energy balance as well. It doesn't partition it into canopy and soil per se like the two-source model does, but it does measure the net radiation, maybe with a net radiometer. I don't have shown here, but there are soil heat flux plates and volume water sensors that are installed into the soil to get the G component of this. And the H and LE terms are estimated with the infrared gas analyzer and the sonic anemometer. We had a non-orthogonal one here. And the idea is that you estimate the sensible heat, at least in terms of the covariance between the vertical wind speed and a proxy of air temperature shown here. And the second one, the latent heat, is similar in that you have a vertical wind speed of this W prime, but it incorporates the water vapor density. It's a covariance between those two. And the covariance is actually averaged over a given time interval. And for this study, we focused on doing that every 15 minutes. And to get a UAV flux from these models, where you have a map of a UAV flux of latent heat at all different pixels, and to get one number that comes from that, what you do is you average all the pixels, UAV pixels in that, based on the footprint that is defined within the towers, which is based on things like the height of the anemometer and the wind speed, and that's how you get a predicted flux from that. So what I'm presenting here, shifting into results now, is the UAV fluxes. How well do they do with the different models as compared with the eddy covariance fluxes? So on the y-axis are those UAV fluxes. In this case, we're just going to be focusing on latent heat. So I also did this for net radiation, and soil and the sensible heat, but just for simplicity, it's to be focusing on the latent heat, which is synonymous or analogous with the evapotranspiration part. We collected UAV surveys from square to bowl filling, so early season to the late season of the vegetation growth, and the points themselves represent the resolution at the 1.05 meters. The closure or the residuals from the eddy covariance towers was less than 20%, and that's in line with what it's been reported within literature is about 80 to 85%. That's this eddy flux tower. It's not a perfect validation tool, but that's what has been acknowledged in literature, and our numbers at least can agree with the other findings as well. So we felt pretty confident as that being a good validation tool. And the two plots, the two panels on the left are the one source model, the dummy model with inputs without inputs and with inputs. So the leftmost one is where you have the weather data removed from the model. So it's just based on that contextual scaling, the Tmax and Tmin. And then this one also does that scaling as well, but it has the weather data used to estimate things like net radiation and the like. So the two source models on the right here, the three panels, the Priestley-Taylor, the dual temperature difference, and the two component temperature. And what I've been finding is that, at least for one growing season and within cotton, the one source model can be more accurate than the two source model. And the other thing I noticed was that when you don't have any inputs, so this plot over here, you have a fairly large bias, about magnitude-wise, about 19%. And then when you do have inputs, essentially those points shift up, and you see that bias reduced by a large amount. And when I say accurate, I mean in terms of the mean absolute error percent. So we're at 15% relative to 30, 24, and 24. And that's my reason for that. And what I wanted to do from that is shift into objective 2, which is we see one source models working particularly well. So I wanted to explore a little bit further as to why that is. Why did it perform as well as the two source models, which requires more data? You'd think it would do better. So to do that, we looked at the scaling properties of the one-source model, which again is based on the n-member criteria from the Tmax or Tmin. So what you're seeing here is the temperature image, the radiometric temperature image for the green is the lowest or the coolest, and scaling up to yellow to orange, which are the hotter ones. The different symbols, let's see if I can do that. The circles represent the native or the 15 centimeter, the hot at 1.05 the squares, and the diamonds are the 10. What you're seeing is that the squares and the circles are pretty much on top of each other, and they're located near the edge of the field. And then when you move to a larger size, the 10 meter, you're essentially seeing it at an entirely different location in a bare soil. That's where that diamond is located. And moving over to the cold member site, you're seeing a similar story being told in that you have, your resolution changing where the end members are located. So this is native, and this is 10 meters, and this is 1 meters. And the reason why I think, they're shifting in space based on the resolution is because of the surrounding environment. So, let's say in this area you have a very localized high temperature, maybe it's like a bare soil, it's like a little patch of bare soil. But you start to, as you get a larger pixel size, you may incorporate some of the edge of the field. So as a result, your Tmax is not your Tmax anymore because it's mixing the hot and cold temperatures. And that's why, at least I think that it shifts, at least for the hot, to a more bare soil or more homogeneous location. And lastly, what I wanted to do is look at how the fluxes compare to each other in terms of the different pixel resolutions. And what you're seeing on the y-axis is UAV, and x-axis, again, the eddy covariance fluxes. What you're seeing is that as you increase the pixel size of your analysis, you're essentially getting a degradation in the quality of your results. So the mean absolute, increases from 14 to 20%. Mean absolute, when you don't have inputs, increases 15 to 27. And what that tells me is that the resolution is going to degrade. You're not going to get good data as you increase that size. And if you think about within the context of how you would use such information, if you wanted to say schedule irrigation based on this ET data, you're not going to use the data at that 15 centimeters. It's just not practical. You can't use that. So there's a practicality beyond just showing that things get worse with size. Is that if you want to apply irrigation on 10 meters, which is generally speaking more feasible, this is something you have to consider, at least with respect to the one source model. So to wrap up, can we model ET using UAV-based data? We can, and what I've been finding, at least within 1 year, is that the one-source models, the dummy temperature models, can outperform two-source, especially with weather data. What is the impact of pixel resolution on model ET, and the accuracy and bias degrade with coarsening pixel resolutions, and the n-member, and that's because of the n-members shifting in space and the mixing of those temperatures, so to speak. So to wrap up, I'd like to thank many people. Some of those people would include those from USDA ARS, so Dr. Bill Kustis, Dr. John Pruger, who provided us with an anemometer and gas analyzer, Dr. Mahanti, who provided us with other sensors, such as the soil heat flux plates or the soil moisture sensors, and manpower for installation. AgriLife, so Dr. Cope, Ian, and Andrew flew the cameras for us and UAVs, and were very flexible. Appreciate them helping us. And Dr. Jung and AJ, who orthomosaic the NDVI images, and then some undergrads and some grads who I don't have listed, who helped collect the agronomic data that facilitated the two-source modeling. So Matt, Michael, and Nicole. And with that, I'll take questions. Thank you.
And so we have time for about 2 questions.
Yes, sir.
So on one of your first couple slides, you talked about having a high and low ET in your field. And generally, what was the mean or the range of your ET there? Was it like you was in decisiemens or?
It was millistemens, and near the towers, the high one was about 90, and the SILT one, the low EC was about 50. The mean in that area is at 40 millistemens.
try looking at the covariance between CO2 and water vapor? Because what I understand about the source models, like you mentioned, looking at splitting up evaporation from the plants versus the soil, if you could compare your estimates from the UAV, partitioning your eddy covariance data, looking at the covariance of CO2 and water vapor, meaning CO2 in the leaf means water vapor out. So that should give you way from partitioning your key data and maybe match up. I was wondering if you look into that.
So there's recent software that allow you to do that. I think we're talking about the same thing. And I think that would be the next step. The problem, or the reason why it's not really addressed here is because if you do such a partitioning, you need something to compare that with, and we didn't have any maybe sap flow sensors or anything else that can help us understand, whether that partitioning itself is correct. That would be, because the problem with that is you have to consider the scale of the sap flow sensors, and that's a whole different set of questions. But to answer your question, we didn't follow up because we didn't have the sensors for one, and second, that we would need to have a different source of validation. I do think it's a good idea though.
Thank you so much.